AP Chemistry, we're now on to Lesson 4 in the Acid-Bases unit, and this is more on weak acids and bases. So we're first going to study something called the common ion effect. The importance of this will become evident later on in this unit. But the previous reaction looked at the equilibrium of a reaction of acetic acid, that's CH3COOH, in pure water to produce the acetate ion, that's CH3COO minus. It lost the proton but not the electron from the hydrogen, and so it now has a negative charge on it. But what if there were some of the acetate ion in the solution before the acetic acid was placed in the vessel, according to the reaction that you see there? Now, it doesn't matter what order you do this. You can put the acetate ion first and then the acetic acid, or the acetic acid in first and then the acetate ion in after that. You're going to end up with the same equilibrium. Equilibrium doesn't care what order you put things in. But nonetheless, what we're dealing with here is a reaction where you already have some of the acetate ion in solution. That's just the easiest way to think of it before the CH3COOH, the acetic acid, is put in there. So if you do that, if you already have some of the acetate ion in, then that's going to make the side of the reaction, the right side, the product side, more crowded. So again, it's the crowded room concept. If you increase the concentration on the right, it's going to push the reaction back towards the reactants. That's Le Chatelier's principle for concentrations. So according to Le Chatelier's principle, increasing the concentration of a product above its equilibrium concentration will cause the reaction to favor reactants and move to the left. What if there were some acetate ion, CH3COO-, in the solution before the acetic acid was placed in the vessel, according to this reaction right here? It's going to favor reactants. So the CH3COO- ion could have come from a substance other than acetic acid. There's other ways to produce an acetate ion. So one of them is a compound called sodium acetate. So look at sodium acetate, CH3COO-Na. If you take away the positive charge of the proton, you have the acetate ion with the negative charge. Remember that sodium, from your rules of your charge numbers of ions, or just how ionic charges work, sodium has a +1 charge. So does a proton. It has a +1 charge. Therefore, sodium, Na, can take the place of the proton at the end of that acetate ion. So now you have CH3COO-Na. That's a neutral compound. In other words, instead of having a positive proton there, you have a positive sodium ion there. That is a neutralized base. The CH3COO- is no longer a base. It now is neutralized. And that's what's called a basic salt. We're going to talk about that later, but that name is not important for now. Just understand that what will happen is that Na dissociates from anything. We learned that from our solubility rules. If you go back and review your solubility rules, sodium, Na, dissolves from anything. It breaks off from anything. So that means that CH3COO-Na will produce an acetate ion, CH3COO- ions, just the same way that acetic acid will. The difference is 100% of the sodium acetate will ionize. The Na will 100% of the time break off and produce acetate ions, whereas acetic acid only occasionally gives up its proton to become an acetate ion. So since CH3COOH and CH3COO-Na both produce an acetate ion, CH3COO-, the effect is called the common ion effect because they both produce a common ion. That is the acetate ion. The common ion effect will prevent the CH3COOH, the acetic acid, from dissociating and will prevent the pH from being lowered. That is, it'll prevent a more acidic solution. So go back up to the reaction up above. If you put in an excess concentration of CH3COO- over on the right, that will push the reaction back to the left. That's the crowded room. It wants to go backwards. Therefore, less of the acetic acid, CH3COOH, will dissociate into hydronium ions. And so that will mean the solution will have fewer hydronium ions and therefore will be less acidic. That will raise the pH of the solution. You just got to kind of stop and think about that for a minute, okay? It doesn't necessarily come through right away. So we're going to set up a rice table. We're going to do a common ion effect reaction here of the same reaction we did in the previous lesson, where we're going to dissociate acetic acid into acetate ions. Okay, so we'll set up a rice table for the weak acid, acetic acid, of 2.1 molar concentration. And then we're also going to have a 2.1 molar concentration of sodium acetate. So first of all, we want to see what happens to the sodium acetate. So we're going to do a rice table for that initially. So here we go. So there you see you have sodium acetate on the left, and it's going to react with water. It's going to produce sodium ions. They're going to be spectator ions. They're not going to do anything else in the reaction. They're just going to sit off to the side and watch the reaction. But then you are going to produce the acetate ion CH3COO-. So we start off with, determine the concentration for the acetate ion produced by the sodium acetate. So we start off with 2.1 molar of sodium acetate. We forget about water. And we initially don't have any sodium ions, and we initially don't have any acetate ions in this solution. We're creating the acetate ions from the sodium acetate. Okay, all of the sodium acetate, 100% of it is going to dissociate. That sodium, Na, is going to break off. And so you're going to end up with 2.1 molar of sodium ions and 2.1 molar of acetate ions. So at the end of this reaction, we have no more sodium acetate. It's all gone. We have a bunch of sodium ions. Again, we don't care about those. Those are irrelevant to this entire reaction. But what is relevant is we end up with 2.1 molar of acetate ions. Now we're going to go ahead. That's the common ion with acetic acid. So now we're going to go on and set up a second rice table. Now, you didn't really have to set up this rice table if you understood that sodium acetate will totally dissociate. So if you put in 2.1 molar of sodium acetate, that's CH3COONA, you're going to end up at the end with 2.1 molar of acetate ions, CH3COO-, okay? So you didn't even have to necessarily do this rice table. Since Na is completely soluble in water, the molarity of CH3COO- and Na+ are the same. That's 2.1 molar as the molarity of the initial concentration of sodium acetate. Okay, so stop and think about that one. You don't have to rush through this. Stop the video and think about that one for a second. Na will not recombine with anything. It is a spectator. It is the concentration of the acetate ion that goes into the rice table in our next rice table. Then that's where we're going to react the acetic acid. Okay, so now we're really starting the problem, the common ion problem. What we were just trying to do before is show you where did that ion come from, that acetate ion come from. If it doesn't come from acetic acid, where does it come from? Well, one place is sodium acetate. So here we go. Now we're going to do the reaction the same way we did in the previous lesson with acetic acid. So step 2, complete the reaction with the acid donating a proton to water to create hydronium ions. This reaction begins with an initial concentration of 2.1 molar acetate ion. So that's where this problem is different from the one we did in the last lesson. So there's the 2.1 molar of acetic acid. Forget about water. You start off with no hydronium ions, but you do start off with the 2.1 molar of the acetate ion. That's from the previous part of this problem, what we just did on the previous rice table. That's where that came from. So this is the beginning of the weak acid reaction with a common ion. This is what we're really interested in. How does this affect the hydronium ion concentration and the pH of the solution by having that common ion, that acetate ion, in there already at the beginning of the reaction? Okay, so here we go. We're ready for the change line. Again, the nice thing about acid reactions is all the coefficients are ones, same with bases. So it's -1 for the acetic acid. Over on the right, it's +1 for the hydronium. Again, you just use the coefficients in front of each of those compounds. And it's +1x, say +1, +1x, +1x for the acetate ion. So now we go ahead and we subtract on the left side. So we get 2.1 minus 1x, or we'll just call it x now. For the H3O concentration, it's 0 plus x is x. And for the acetate ion over on the right, it's 2.1 plus x. And that's 2.1 plus x. Okay, now we're ready to write the law of mass action. So go ahead and do that. Think about what that's going to look like here. And there it is. So convince yourself the products on the right side are on the top. They both have coefficients of 1, so there's no exponent. And the reactant, the acetic acid over on the left, is down on the bottom. And you don't include a pure liquid, water, in the law of mass action. So that's the law of mass action. So now you're ready to substitute those algebraic expressions down in the equilibrium line. Okay, and we can substitute also our Ka value, which we were given in the problem up above. So there we go. So there's Ka is 1.8 times 10 to the negative fifth. And then up on the top you have x times 2.1 plus x. And down on the bottom you have what's on the reactant side, 2.1 minus x. So the simplifying assumption says that both that plus x and that minus x are much smaller than 2.1. So they both disappear. That plus x on the top and that minus x on the bottom both go away. Because they're so much smaller than 2.1, we can ignore them. So the simplifying assumption states that if the value of x is much smaller than the initial concentration, 2.1 molar in this case, then x in the 2.1 minus x can be eliminated, and also the x in the 2.1 plus x can be eliminated. And the assumption must be justified at the end of the problem using the 5% rule. So there we go. That's the same equation we had on the previous slide. And now those x's go away. So now we have on the top 2.1 times x over 2.1. So convince yourself of the algebra on that. And now the math is pretty simple. The 2.1s both cancel out on the right side. So solving for x, 2.1s cancel out, and you get x equals 1.8 times 10 to the negative fifth. So that's your value of x. And if you look up on the equilibrium line in the rice table, that's also your value for the hydronium ion. And that's what's going to determine the pH. Remember, it's the hydronium ion, H3O plus, that determines the acidity of solution. It's how many of those H3O pluses you have in the solution. Okay, so now we calculate the concentrations. This problem really didn't ask for any one concentration or pH or pOH, because we're going to go ahead and calculate all of them. But it might have just asked for the pH or the hydronium ion concentration or just one thing. Let's go ahead and just start calculating things. Okay, so first of all, we really don't care about the acetic acid over on the left side, but if we wanted to know that, it would be 2.1 minus x. Well, x equals 1.8 times 10 to the negative fifth, so think about that. 2.1 equals 2.1 times 10 to the 0 power, because 10 to the 0 equals 1. Whereas, so you have a 10 to the 0 power versus a 10 to the negative fifth power. That's a difference of 100,000 times. So basically the 2.1 is 100,000 times bigger than 1.8 times 10 to the negative fifth. So when we said x is much, much less than 2.1, and so we could ignore it, we can. You'll see that 2.1 minus 1.8 times 10 to the negative fifth basically equals 2.1. You could ignore that x. Now let's go on. H3O plus. That's easy because we know the value of x, and x is the hydronium ion concentration. So it's simply 1.8 times 10 to the minus fifth molar. Finally, we can figure out the acetate ion concentration, and that's CH3COO minus. So it's 2.1 plus x. Well, again, the x is so small compared to the 2.1, you can ignore it. The 1.8 times 10 to the minus fifth can be ignored, so it basically equals 2.1. Okay, now we can go ahead and calculate the OH minus, the pH, and the POH as requested by the problem. Well, the problem didn't request any of those, but we're solving for all of them. So here we go. So the OH concentration, how do you get that? It's the hydronium ion concentration times the OH concentration equals 10 to the minus 14th. So we know the H3O concentration. So to get OH, we divide 10 to the minus 14th by our hydronium ion concentration, X, 1.8 times 10 to the negative fifth. And it gives us a hydroxide ion concentration of 5.6 times 10 to the negative 10th. Okay, now's really the punchline of this whole exercise. Let's figure out the pH. So it's the negative log of the hydronium ion concentration, 1.8 times 10 to the negative fifth, and that gives you a number of 4.7 for the pH. So in the common ion effect problem that we just did, the pH is 4.7. And then of course POH, if you want to calculate that, POH plus pH equals 14. So that means 14 minus the 4.7 pH equals the POH, which is 9.3. So here's a summary. The pH of the acetic acid in pure water, this is what we did in the last lesson, was 2.2. You go back to the last lesson, you can see that. We calculated a pH of 2.2. The pH in this problem with the acetic acid reacted with already some existing acetate ion in solution, the common ion, is 4.7. So what does that higher pH number mean? It means that the solution is less acidic. Remember, higher pH means less acidic solution. Lower pH is more acidic solution. So what that means is, why is that? Because the acetic acid, CH3COOH, had a common ion over already in the solution, it could not dissociate as easily. It could not create hydronium ions, H3O plus ions, as easily, because it was already too crowded over on the product side with that acetate ion that was already there. And therefore, less of the acetic acid dissociated into not only acetate ion, but hydronium ions to make an acidic solution. So the common ion caused the acid, the solution to be less acidic. So here's a little graphic. So every CH3COONA molecule breaks up into an Na plus and an acetate ion, CH3COO minus. So there you have that. So now you have 2.1 molar of acetate ion, CH3COO minus. So there they are. They're already existing in the solution before we even put the acetic acid in. So too much acetate ion pushes the reaction back to the left according to Le Chatelier's principle. Pushing the reaction to the left means that the acetic acid, CH3COOH, cannot dissociate, or not dissociate as easily. This decreases the hydronium ion concentration and raises the pH from 2.2 up to 4.7. So that's the effect of a common ion. Okay, and we will see the significance of common ion reactions later on in this unit. Okay, now we're going to move on to weak base reactions. We've dealt so far only with weak acid reactions. Weak base reactions are very similar. So we're going to compute everything here, the whole table here. pH, POH, OH minus, and H plus, H3O plus, same thing, of a 3.2 molar concentration of a weak base, C5H5N, which has a Kb. Now notice this is a Kb. When you do a base reaction, you have to use the Kb. Now here's the problem. In many books, you're not given Kbs in the list of tables in the back of, say, your textbook, for example. You're given a Ka. So how do you deal with that? Well, we'll talk about that more later, but basically it comes down to this, that Ka times Kb equals 10 to the minus 14th. So if you know Ka, you can simply divide 10 to the minus 14th by Ka, and that will give you the Kb. But you got to remember that to do a base reaction, you have to use the equilibrium constant for base, called the base dissociation constant, which is Kb. Okay, so here's our rice table. So let's look at how this reaction looks. If that's a base, it's going to accept a proton from the water molecule. So what happens is you put the base in there and with the water, and then what happens is a proton jumps from the water molecule over to that weak base to make it C5H5N and then an H+. Okay, so it gained a proton, it accepted a proton. That's what bases do. What it left behind in the solution is that broken water molecule minus that proton, which is called a hydroxide ion, or OH-. Okay, at this point then, the hardest part might be to be sure you recognize which is a base and which is an acid. When it's a base, how do I know if it's a base or an acid? By looking at it. Sometimes you won't. So you learn from experience. Oftentimes the problem will state clearly it's a base reaction. But what you want to do is learn to write the reaction properly. Okay, so this is how you would write a base reaction. Okay, so we're ready to go ahead and put in our numbers. We start off with 3.2 molar C5H5N. We ignore the water. And then over on the right side, at the beginning, this is not a common ion problem, okay? So kind of put that out of your mind from the previous problem that we did. It's going to be 0 and 0 to start with over on the product side. Okay, now everybody's got a coefficient of 1 here, so it's going to be let me just read that then. Since no concentration values are given for C5H5, NH+, and OH-, we can assume they're 0. Okay, now we're going to go on and do our change line. Okay, so all the coefficients are 1, so it's minus 1x, plus 1x, plus 1x. Okay, so down below, it's just simply a subtraction on the left and addition on the right. So the reactant C5H5N shows a negative sign because it is decreasing in concentration. The coefficients in front of the x variables are the same as in front of the reactant and products above, which are all 1s. Water is not included since it is a pure liquid. Okay, so here we go. So we're going to subtract on the left 3.2 minus x. On the right, it's 0 plus x is x, 0 plus x is x. Starting to look familiar, hopefully, to you, how these change lines all kind of look the same. And this is even a base reaction. Whether it's an acid or base reaction, they all look the same. Okay, so we have our base dissociation constant over there. So we write the law of mass action. If the value of Ka had been given, you would need to convert it to Kb. And I just talked about how you do that using 10 to the minus 14th. So there's the law of mass action. Convince yourself that that's correct. So now we can go ahead and plug in the algebraic expressions into that. So substitute algebraic expressions on the equilibrium line into the equation and substitute the given value for Kb. So there it is. So convince yourself that that's correct. And again, we can use the simplifying assumption for that x in the denominator, so it goes away. So the simplifying assumption states that if the value of x is much smaller than the initial concentration, 3.2 molar in this problem, then the x in 3.2 minus x can be eliminated. Okay, the assumption must be justified at the end of the problem using the 5% rule. Honestly, I don't do that on these lecture problems, but we'll do it in some of the problem set problems. Okay, so there it is, the same equation. And there goes that x on the bottom, so it's just a 3.2, and the x times x becomes x squared. So now it's a pretty simple algebra problem. Okay, so there it is. Multiply 3.2 on both sides, cancel, and you get 5.44 times 10 to the minus 9th equals x squared. Take the square root of both sides, and you get x equals 7.38 times 10 to the negative 5th. Okay, so that's our value of x, and as you look up at the equilibrium line of the rice table, you can see that's also the concentration of hydroxide ions. Remember, bases are going to produce hydroxide ions, OH-. So that's really the compound, the substance that we're interested in. So X represents OH minus equals 7.38 times 10 to the negative fifth. Okay, calculate the concentrations. Okay, so now we can figure out POH and pH. We know hydroxide, and we can figure out the hydronium ion concentration as well. So the concentration of the original base was 3.2 minus X. You see that from the equilibrium line down below C5H5N. So X is very, very small again. It's 10 to the minus fifth is 100,000 times smaller than 3.2, so you can ignore it, and you basically get 3.2. Effectively, out to the about fourth or fifth significant figure, the concentration hasn't changed. Okay, now we have our conjugate acid. C5H5NH plus is the conjugate acid of the base C5H5N. That's the conjugate acid. And that's X, and that's 7.38 times 10 to the negative fifth. And the OH concentration is also that same number. Okay, so now we can calculate the H3O plus pH and POH. So H3O plus times OH minus equals 10 to the minus 14th. We divide both sides by the OH minus, and we get a hydronium ion concentration of 1.4 times 10 to the negative 10th. Now we can compute the pH. It's the negative log of 1.4 times 10 to the negative 10th, and that gives us 9.9. So that's well above 7. That's well up into the base range. And so that's your pH. It is definitely a basic solution. It has hydroxide ions in it, so the pH is going to be above 7, which is neutral. It's going to be up high, and that's going to be in the base range. And then, of course, we can figure out the POH. It's pH plus POH equals 14. Subtract the 9.9 from 14, and you get a POH of 4.1. So again, you do a weak base reaction exactly like a weak acid reaction. The only difference is you have to recognize that it's a base reaction versus an acid reaction, and you have to be sure to use the base dissociation constant Kb. And that takes care of our lesson on the common ion effect. Common ion effect can be used with both acids and bases. Our example did it with an acid. And then we showed a weak base reaction, which is done exactly the same way as weak acid reactions. So just practice about 5 of these, and they will become very natural for you. Okay, we'll see you on the next lesson.